A long solid non-conducting cylinder of radius 10 cm contains a uniformly distributed charge of density 10 nanocoulomb per meter cube. Find the magnitude of electric field at a point P inside the cylindrical volume at a distance 5 cm from its axis. Okay, so we have a solid cylinder which is non-conducting, means the charge can be everywhere inside its body. Okay, and the radius is 10 cm. We have to find out the electric field at a point which is at a distance 5 cm from the axis. So this point is inside the body of the solid cylinder. Alright, so obviously we're going to use Gauss's law, and to choose the Gaussian surface we have to keep these 2 points in mind. Alright, so let's do it. So again, this is a infinitely long solid cylinder. Okay, so if that is the case, we know that the electric field is going to be perpendicular to the charge distribution. Okay, since it is a cylinder, perpendicular to the charge distribution is going to be in the radial direction. All right, we have seen that already. So the correct Gaussian surface, or the useful Gaussian surface, is going to be another smaller cylinder whose axis coincides with the axis of the large cylinder, which has a radius r, which passes through this point P and has a length L. Okay, if this is the situation, we know that the electric field is going to be radial in nature. Okay, and we can see that every point on the surface of the cylinder is symmetrical to the charge distribution. Hence the magnitude of electric field is going to be the same at all points. Also, the area vector is going to be perpendicular to the surface and hence parallel to the electric field. So it is making 0 degree. Another important thing is that this surface has an area vector in this direction. This surface has an area vector in this direction. So it is making 90 degree with the electric field. Hence the flux through the top and the bottom surface is going to be 0. Okay, so if we write Gauss's law, which is closed integral of E dot dA is equal to Q inside upon epsilon naught, we know that the top and bottom surface, there will be no flux. So it just boils down to the flux through the curved surface. So integral of E dot dA is the flux through the curved surface. This is equal to Q inside upon epsilon naught. Alright, so this is going to become E dA, and we have seen that at every point dA and E is making 0 degree, because E is also radial and dA is also radial. So this becomes cos 0 degree is equal to Q inside upon epsilon naught. E is going to come out, and the integral of dA would be the integral or the total area of the curved surface, and that is going to be 2 pi r into L. Alright, this is equal to Q inside upon epsilon naught. Now this is interesting because this is a solid cylinder. The charge is everywhere inside, inside its body. So what is the charge enclosed inside? It is the charge which is in this entire volume. So we have to find the charge which is enclosed in this entire volume of the Gaussian surface. Okay, so we know charge per unit volume. So how are we going to find the total charge? It will be the charge per unit volume multiplied by the volume. What is the volume of this cylinder? It is going to be pi r square multiplied by L. Alright, the area into the height of the cylinder. That is it. So L gone, R, 1r gone, pi gone. So we are left with E is equal to rho r upon 2 epsilon. Sorry, I missed the epsilon naught here. Q enclosed upon epsilon naught. So E is equal to rho r upon 2 epsilon naught. Now all we need to do is do the substitution. What is rho? 10 nanocoulomb per meter cube. I'll have to multiply it by 10 to the power minus 9 to make it SI units. Multiplied by small r, which is 5 centimeter. I'll have to convert that to meter. Divided by 2 into epsilon naught is approximately 9 into 10 to the power minus 12. Alright, so what do we have here? This 10, and then we'll have 10 to the power minus 1. Now 10 to the power minus 9 and 10 to the power minus 1 is going to make 10 to the power minus 10. And when this goes upstairs, this is going to become 100. So 2 and 50, so we are left with 250 divided by 9. And if we do the simple calculation, we are going to get approximately 27.8 Newton per coulomb. That is going to be my answer. Let's have a look at the options. So option B is going to be the correct option. So you see that choosing the Gaussian surface is 90% of the job. After that, it's just simple calculation. All right, let's proceed. All right, another interesting situation. So find the electric field due to an infinitely large, uniformly charged, non-conducting thick sheet at a point P inside as shown in the figure. Alright, so again it is non-conducting thick sheet, which means that the charge is in its entire volume. It is infinitely large, that is something we should note as well, and this point is inside this thick sheet. Alright, so the trick again is to find the Gaussian surface. So we should have some idea of the direction of electric field. Now again, this is an infinitely large plane sheet of charge, which means that the electric field should be perpendicular to the charge distribution. Okay, the charge distribution is like this, like a sheet. So the electric field has to be perpendicular to that. Correct? So a very smart way of choosing a Gaussian surface would be a cylinder like this. Okay, so the cylinder has a length 2x, which is symmetrically placed across the central line. Okay, and one of its surfaces is passing through this point. All right, so we have already established that the electric field is going to be perpendicular to the charge distribution. So the electric field is going to be something like this. Okay, now why is this surface useful? Why is this Gaussian surface useful? Let's analyze that. So if we talk about this surface, the area vector is going to be like this, which is making 0 degree with the electric field. This surface, the area vector is going to be like this, which is again making 0 degree with the electric field. And we have a curved surface. Now the electric field is along the axis. Any point on the curved surface is going to be perpendicular to the axis. So the flux through the the angle between the area vector at any point on the curved surface and the electric field is going to be 90 degree. Okay, so this is a perfectly chosen Gaussian surface. So now all we need to do is do the calculation. All right, let's do the calculation quickly. Now let's say this surface has an area A. This surface, this cross-sectional area I'm talking about, has a surface area A, and the electric field is E. Now we have already established that the magnitude of electric field is going to be the same at all points of the surface. Why? Because it is symmetrical across about the charge distribution. All right, so electric field E, area A. So the flux through this surface is going to be E into A, because area vector is making 0 degree. Correct. Here also the area vector is making 0 degree. So EA cos 0 degree is simply EA. So EA on this surface, again EA on this surface, so this becomes 2EA. And then what is the flux through the curved surface? This is perpendicular. The area vector is perpendicular to the electric field, hence it is 0. So the net flux through this Gaussian surface is simply 2E into A. All right. Now what is Q inside? Okay, so the Q inside is going to be this volume. This charge is going to be distributed throughout this volume. So the Q inside is going to be the volume of the Gaussian surface, this cylinder, multiplied by the charge per unit volume. So charge per unit volume is rho. What is the volume? The volume here is going to be the area of cross section into the length. What is the length? The length is 2x. So A into 2x. So the total flux is equal to Q inside upon epsilon naught. So this A and this A gone, this 2 and this 2 gone. So E is equal to rho x upon epsilon naught. Alright, that is my result. Now all I have to do is do the substitution, find the answer. So this is going to be rho, which is 9 into 10 to the power minus 9 coulomb per meter cube, into x is 1 centimeter, which is 10 to the power minus 2 meter, divided by epsilon naught, which is 9 into 10 to the power minus 12 SI units. Okay, so this 9 and this 9 gone. This is 10 to the power minus 11. This will go upstairs and make it 10. So my final answer is going to be 10 Newton per coulomb. What is the correct option? Option D is the correct option. Find the electric field at a point P as shown in figure due to an infinite long uniformly charged non-conducting thick sheet. Okay, so we have a thick sheet again, but where is the point? The point is outside. All right, it is not inside the body of the sheet. Okay, it is outside, but the concept remains the same. We know this is infinitely large, so the electric field is going to be perpendicular to the charge distribution. Hence, it is going to be like this, perpendicular to the sheet, surface of the sheet. Okay, so the correct way of choosing a Gaussian surface would be like this. Okay, again the length of this cylinder is 2x and it is symmetrically placed about the central line. And we know that the electric field is going to be like this. We have already discussed it. And since the situation is absolutely symmetrical at all points, the electric field, the magnitude of electric field is going to be the same. All right, perfect. So this is the situation. Now let's do the calculation. All right, so electric field is like this. Area vector for this surface is going to be like this. Okay, let's say the magnitude of the area is A, the magnitude of this area is also A, and then we have a curved surface area. So here also the area vector is going to be like this. So closed integral of E dot dA is equal to Q inside upon epsilon naught. Perfect. So we have three surfaces. Through this surface, the flux is going to be E into A. Why? Because the angle is 0 degree. The angle between the electric field and area vector is 0 degree. Through this surface as well, the flux is going to be EA. So this becomes 2EA. And through this curved surface, what will be the flux? Yes, it is going to be 0 because the area vector in this situation is going to be perpendicular to the surface, which means perpendicular to the axis, and the electric field is along the axis. So the flux is going to become 0. So the total flux is 2EA multiplied by Q inside upon epsilon naught. Okay, now be very careful. Here we have to calculate the charge inside. Now we see that this Gaussian surface we have chosen, some part of the Gaussian surface is overshooting, or it is outside the charge sheet. Is that correct? So if I talk about this situation, the charge is only enclosed within the width of the sheet. So the width of the sheet is D. So the charge is only enclosed within the width of the sheet. This part here and this part here is not going to have any charge. That is the difference with the last problem. All right. So if this is the situation, what will be the Q inside? It will be the charge inside this volume. Okay. What about this volume? It has an area of cross section A and it has a length of D. Okay, so this is going to become rho, which is charge per unit volume, into the volume. Volume is going to be D multiplied by what? Multiplied by the area divided by epsilon naught. Okay, so A and A gone. We have E is equal to rho D upon 2 epsilon naught, and that is going to be my answer. Okay, so sorry, that is not going to be my answer. That is my expression. Now I have to substitute and find the answer. Not a big deal at all. So rho is going to become 9 into 10 to the power minus 9 coulomb per meter cube. D is 4 centimeter. So I will have to convert that to meter. Divided by 2 into epsilon naught is approximately 9 into 10 to the power minus 12 SI units. 9 and 9 gone. 2 and 4, 2 remains. And this is minus 11, minus 12. So I have 10 upstairs. So my final answer is going to be 20 Newton per coulomb. And let's have a look at the options. So option B is going to be the correct option. A charge Q is placed at point O in a cavity in a spherical uncharged conductor. Point S is outside the conductor. If Q is displaced from O towards S such that it is still inside the cavity, then the electric field at S will increase, decrease, first increase and then decrease, remain unchanged. All right, perfect. Now this is a very, very important concept, extremely conceptual topic. So let's first understand the key concept here. Okay, so we have an uncharged conductor. Inside that there is a cavity and we have placed charge Q. Now if we take a Gaussian surface through the meat of the conductor, we know that through the meat of the conductor the electric field is 0. Okay, so if electric field is 0, the flux through this Gaussian surface is 0, and the flux is given as Q inside upon epsilon naught. So if the flux through this Gaussian surface is 0, then Q inside must be 0. Okay, which means that if there is a charge Q, then on the inner surface of the conductor there must be a charge minus Q. Okay, so that the net charge inside is 0. Perfect. Now this conductor is uncharged. It is isolated as well. If it is isolated, from where is it going to get charge? There can be no exchange of charges. Okay, so if it was uncharged, it will still remain uncharged. So if minus q has appeared on the inner surface, then necessarily plus q has to appear on the outer surface. All right, perfect. Now, whatever is the charge distribution, their main objective is always to make the field inside the conductor zero. Okay, but there is a consequence of that as well. Now, we are dividing the charges into two parts. Now, this q and this minus q are internal charges. They're inside the cavity. We're going to call them internal charges. And this plus q is external charge. Okay. Now, what is going to happen is that these internal charges are going to be such distributed that they make the field zero inside the conductor. Okay, and the consequences of that is that they are going to also make the field everywhere outside zero. Okay, so internal charges are going to make the field zero inside the conductor and everywhere outside as well. All right. And these external charges, they are going to be distributed in such a manner that they also make the field zero inside the conductor, and the consequence of that is going to be they are going to make the field zero inside the cavity as well. Okay, so I'm repeating this. External charges will make the field zero inside the conductor as well as everywhere inside. Internal charges are going to make the field zero inside the conductor as well as everywhere outside, which basically means any point which is outside will have no impact from the internal charges. They are only going to get impacted due to external charges. And similarly, any point inside is only going to get impacted by internal charges and not by external charges. And this is the beauty of electrostatic shielding. Okay. So the external point is shielded from the internal charges and the internal point is shielded from the external charges. This is electrostatic shielding. All right. Now let's use this concept to solve this question. Okay. So we know that there is going to be charge minus q and charge plus q on the outer surface. Minus q on the inner surface, plus q on the outer surface. Now in this situation, this q and minus q is already making the field zero over here. Okay. And the field here is only because of this external charge. Okay, I'm repeating, this internal charge is going to have no effect externally. So the field at point S is only going to be due to the external charge. Okay, perfect. Now the external charge is so configured, the distribution of external charge is such that it is making the field zero inside the conductor, and the consequence is that it is also making the field inside zero inside the cavity. Okay, perfect. Very good. Now if we move this charge a bit, let's say we move this charge q a bit, then the charge inside or on the inner surface of the conductor is going to change such that the field inside the conductor becomes zero again, and still the field at an external point due to internal charges is still going to be zero because internal charges have no effect outside. So the field on S is still going to be because of the external charges only. Now the external charges had a certain configuration which made the field zero inside the conductor. Okay, its job is to still make the field zero inside the conductor. Okay, so should the configuration of the external charge change? It should not, because it is already doing its job. And if the charge configuration of the external charge does not change, should there be any effect on the electric field at an external point? The charge distribution hasn't changed, so the field is also not going to be changed. All right, so what is going to be my answer? It is going to remain unchanged because we are only changing the internal charge configuration. The external charge configuration is going to be remaining intact. Okay, so that is going to be my answer, remain unchanged. And let's have a look at the options. So option D is going to be my correct option. A thin metallic spherical shell contains a charge q on its surface. A point charge q1 is placed at the center of the shell and another charge q2 is placed outside the shell. All the three charges are positive, then the force on charge q1 is. Alright, this is the situation. The concept here again is electrostatic shielding. And what does it tell us? That in a conductor, the distribution of charge is such that the electric field due to internal charges is zero inside the conductor as well as outside. The electric field due to external charge is zero inside the conductor as well as inside. Okay, so external charges don't have any influence inside and internal charges don't have any influence outside. This is the basic key concept of electrostatic shielding. Now let's try to solve this question. Okay, so we have a charge plus q1 here. Now if we take a Gaussian surface through the meat of the conductor, then we know inside the conductor the electric field is 0, so electric flux is going to be 0, so the net charge inside is also going to be 0. Okay, so we'll have charge minus q1 distributed on the inner surface. Okay, so that plus q1 and minus q1 give us 0 charge. Now this conductor is isolated, so the net charge has to be conserved. So initially it has plus q charge, so finally also it should have a total of plus q charge. Now on the inner surface there is minus q1 charge, so what should be the charge on the outer surface? It should be q plus q1, so that this charge and this charge together gives us plus q. Alright, so this is going to be the charge distribution. Now one thing is for sure, that if q1 has to experience a force, then at the center there has to be electric field. If there is electric field, then it is going to experience force. So we need to find out what is the electric field here. Okay, perfect. So this is external charge. This q plus q1 is also external charge, and what we have learned just now is that external charges have no influence inside. So the electric field due to the external charge is going to be 0. Is that correct? So these two external charges are not going to apply any force on q2. What can apply force on q2 is minus q1. Okay, let's understand, will that apply a force or not? Now the job of internal charges is to make field 0 inside the conductor. Okay, so this is a point charge q1, and let's talk about this point inside the conductor. Let's say the radius is r. So the field due to plus q1 is going to be kq upon r, kq1 upon r square in the outward direction, which means that this minus q1 has to cancel this field. If it has to cancel the field, then it has to have a field kq1 upon r square in the opposite direction. Okay, so the magnitude of field has to be kq1 upon r square. Okay, when is this possible? It is only possible that if this is a uniform spherical charge distribution. Okay, for a spherical, uniformly charged spherical shell, the field at this point at a distance r is going to be kq upon r square. Okay, if this is non-uniform, then it is not going to be kq1 upon r square. So in order to make the field 0 inside the conductor, this minus q1 has to be uniformly distributed over the surface of this spherical shell. Okay, that is the key catch in this problem. Hence we know that we have an internal charge which is uniformly distributed, and it is making a uniformly distributed spherical charge distribution. What is the field inside a uniformly distributed spherical charge distribution? It is 0 at all the points. So what will be the field at the center? It is also going to be 0. Okay, so external charges already did not have any field inside, but the internal charge also was such distributed that it was making the field 0 inside the conductor, and the consequence of that was that it was also making the field 0 at the center of this spherical shell. Okay, so what is the net field at the center of the shell? It is going to be 0, hence it is going to experience a force equal to 0, and that is going to be my answer. All right, you see, extremely conceptual problem we just solved. Okay, so the correct option is going to be option C.